Training a frontier AI model today feels honestly less like writing software and more like building a particle accelerator.
Yeah, it really does.
It's this massive, multi-billion-dollar physical undertaking, and suddenly it's a matter of intense geopolitical statecraft.
It's a total paradigm shift. I mean,
Right.
the sheer physical footprint of compute has transformed lines of code into, strategic national assets.
Right.
And when access to that hardware becomes a geopolitical bottleneck, the software is forced to adapt in some truly fascinating, hyper-efficient ways.
Which brings us to the core of what we're unpacking today. So if you're a data scientist navigating this space right now, in this final week of July 2026, you're caught right in the middle of this shift.
Exact.
We're cutting through all the geopolitical noise and the benchmark hype to pull out the exact parameters, the agentic frameworks, and the actionable efficiency hacks that are actually going to impact your daily machine learning pipelines.
Because that's what really matters on Monday morning.
Right. So we're going to look at the macro scaling battles, defining the hardware landscape, how developers are bypassing those limits with highly efficient agentic architectures, and finally, how you can run just staggering visual world models right on a single GPU.
Yeah, and you really can't understand the software breakthroughs of this week without first looking at the hardware constraints.
Definitely.
And there's really no clearer example of that tension right now than the massive controversy surrounding Moonshot's Kimi K3 model.
Right. Let's unpack that, because benchmarks are basically becoming geopolitical battlegrounds at this point.
Oh, 100%.
We reviewed a recent cyberattack benchmarking study, and it noted that the Chinese model Kimi K3 scored 32.2% in cyberattack capabilities. And the report explicitly contrasts this with unnamed top U.S. models that are averaging like 76.2% on those exact same benchmarks.
It's a really stark contrast in the data, but it immediately sparked this massive debate in the research community.
Oh, yeah, huge pushback.
Right. Global AI experts are pushing back hard against U.S. claims that Kimi K3 relies on intellectual property theft or distillation from American models.
Yeah, they're pointing to actual engineering.
Exactly. They're pointing to Kimi K3's legitimate technical innovations, specifically its 2.8 trillion parameter scale and its reliance on MXFP4 quantization.
I want to pause on those cyberattack benchmarks for a second, though, because a 32 versus a 76% is a huge gap.
It's massive.
But is measuring a model's cyberattack capability like comparing a Swiss Army knife to a dedicated lockpick?
That's a really good way to put it.
Right. Meaning, do these specific benchmarks actually measure raw intelligence, or are they just measuring highly specialized red teaming alignment that U.S. labs just heavily prioritize?
That's exactly the question researchers are raising.
Yep.
Are we testing general capability, or are we testing a model's refusal rates and specialized offensive training?
Right. And we need to be crystal clear for you listening. We are strictly reporting on the viewpoints presented in our source material here.
Yes, absolutely.
We aren't endorsing the claims of either side in this U.S.-China tech war. We're just looking at the sources. But what is undeniable is the technical reality of how they are scaling.
Yeah.
You mentioned MXFP4 quantization. This is where the engineering gets brilliant.
It really is.
Yeah.
Because an XFT4 is a sub-byte quantization format.
So it's a direct strategy for maximizing memory bandwidth, isn't it?
Exactly. MXFT4 packs weights into just 4 bits. In the physical reality of a GPU, compute speed often isn't your bottleneck, memory bandwidth.
Well, you spend more time moving data around than actually calculating it.
Exactly. So by using 4-bit quantization, you are effectively doubling the amount of data you can push through the memory bus per clock cycle compared to 8-bit formats.
Wow.
It's a direct physical response to hardware limitations.
And speaking of hardware limitations, we really have to look at what Huawei is doing.
Oh, yeah.
Ren Zhengfei, Huawei's founder, came out this week aggressively backing what they call the Tau scaling law.
Right. So the Tau scaling law is essentially Huawei's strategic framework to bypass the lack of extreme ultraviolet, or EUV, lithography.
Because of the sanctions?
Right. Because of U.S. sanctions, Huawei can't access the ASML machines required to print the smallest, most advanced transistors on a chip.
So they hit a physical density limit on the silicon itself.
Exactly. They hit a wall.
So if you can't build a denser, faster chip, how does the Tau scaling law actually work, mathematically or architecturally to keep scaling the AI?
Well, think of it like city planning. If you aren't allowed to build skyscrapers to increase your city's density.
Which is the EUV limitation.
Right, exactly. Then you have to build a massive, perfectly synchronized transit system between a bunch of smaller cities.
Oh, okay.
The Tau scaling law focuses intensely on cluster interconnects and distributed scaling architectures. It's about how you network thousands of slightly less capable chips together so efficiently that the software experiences it as one massive supercomputer.
That's fascinating. It's a completely divergent evolutionary path for compute.
It really is.
Which perfectly sets the stage for the open weight model debate we saw in the sources. Nvidia, Palantir, and Meta published an open letter this week,
Yeah, that was a big deal.
urging U.S. policymakers to avoid, quote, premature restrictions on open weight models.
Right.
Their argument is that if you lock down American open weights, you don't actually stop AI proliferation. You just stifle domestic competition and drive developers globally straight into the Chinese AI ecosystems we just talked about.
And the underlying logic there is that because hardware is so bottlenecked by these geopolitical sanctions, the software, the model weights themselves, have become the primary vector for global influence.
Right. And because scaling these massive frontier models is becoming this intense geopolitical battleground, the average developer is realizing they can't just rely on throwing more H100s at a problem.
No, you can't.
We are being forced to extract significantly more power from smaller, smarter systems.
Which is exactly why we saw an absolute explosion this week in agentic architectures and serving systems. Developers are basically pivoting from raw scale to extreme efficiency.
Let's talk about SearchOS v1, because this tackles a massive pain point for any data scientist who has tried to build an information-seeking agent.
Oh, we've all been there.
Right, we've all seen it. The agent gets trapped in a repetitive search loop. It tries a query, fails, completely forgets the context of why it failed, and then stubbornly tries the exact same query again.
It's infuriating. But SearchOS v1 supposedly solves this by turning implicit search progress into explicit state.
Right.
It uses a framework called Search-Oriented Context Management, or SOCM.
Okay, I have to push back here a little bit. Isn't this just giving the LLM a scratch pad? I mean, we've had chain of thought and scratch pads for a long time.
Yeah, I get why you'd think that, but it's much more robust than a simple scratch pad prompt. SearchOS v1 is an actual system-level middleware harness.
Oh, really?
Yeah, it sits between the model and the environment, actively intercepting tool interactions. SOCM explicitly externalizes the search state into 4 mathematical components.
Okay, what are they?
A frontier task, an evidence graph, a coverage map, and crucially, a failure memory.
So how does that failure memory physically stop the loop? Is it just like a text list of bad searches?
No, it maps out the dead ends into the agent's contextual state. When the agent fails to find evidence, the middleware forces it to log the exact semantic failure path.
Okay.
So when it formulates the next query, the coverage map and failure memory act as a strict constraint. It physically cannot repeat the same mistake because the middleware scheduler steers the retrieval path away from that mapped dead end.
That makes a ton of sense. And the sources note it uses pipeline parallel scheduling for the sub-agents.
Yes.
So rather than waiting for one agent to finish a complex multi-step search before starting the next task, it's constantly subbing in new tasks the second a compute slot opens up. It's kind of like a high-end restaurant kitchen where the expediter isn't waiting for the sous chef to finish the entire meal. The second a cutting board is clear, they are prepping the next ticket to maximize the kitchen's total output.
That's a great analogy.
Yeah.
It maximizes total throughput and prevents budget exhaustion by treating agent search like an operating system scheduler.
Right.
And we're seeing the same rigorous structuring move from web search right onto the desktop with no-act UI claw.
Oh, this one is fascinating. Their operating paradigm is know deeply, act perfectly.
Yeah, I love that name.
We've seen previous graphical user interface automation frameworks like OpenClaw, but they had serious deficits. I mean, they'd break the second you move them from Windows to a mobile environment.
Right, they were super fragile.
But no-act UI claw gives agents self-evolving skills and what they call experience attributable memory.
And that experience attributable memory is the key differentiator. Normally, if an agent clicks a button and fails, it just gets a generic error. But no-act UI claw tags the specific success or failure to the underlying UI hierarchy of that exact application.
Oh, wow.
So over time, the agent actually learns the structural logic of the operating system itself, whether it's Android, iOS, HarmonyOS, or Windows.
And the performance data actually backs it up. It achieved a record 64.1% on the Mobile World benchmark. And the kicker here, it did this using the open source Kimi 2.6 model And it actually beat closed proprietary models like GPT 5.5 at desktop automation.
Which is wild. It proves that you don't always need a massive centralized frontier model. If your local agent architecture can remember its mistakes and map the UI environment effectively, a smaller open-weight model can outperform a behemoth.
And the infrastructure layer is evolving to support this rapid local training too. The sources highlight that on-policy distillation, or OPD, is now being integrated directly into serving frameworks like Miles and SGLang.
This is a huge quality of life upgrade for developers. On-policy distillation tightly couples the generation of data with the training of the smaller model.
Right.
By integrating OPD directly into the rollout flow of Miles and SGLang, you can train these highly efficient student models on the fly.
While the agent is actually interacting with its environment.
Exactly, drastically reducing the overhead required to create specialized agents.
Well, if no-act GUI claw proves that we can optimize an agent to perfectly navigate the 2D space of our desktops, the natural next frontier is the 3D space.
Absolutely.
Which brings us to the astonishing efficiency we're seeing in world models and visual generation this week.
The push for compact efficiency in the visual space is moving just as fast as the agent space.
Right.
And MageFlow is the standout example here.
Yeah, MageFlow.
It's a highly compact visual generation stack running on just 4 billion parameters.
Okay, wait. 4 billion parameters for a state-of-the-art visual stack is tiny. We're talking about LLMs with 2.8 trillion parameters.
I know, it's crazy.
How does a model this small punch so far above its weight? The paper mentions two things: a co-designed Mage VAE and a multimodal diffusion transformer trained with rectified flow matching. Walk me through the mechanics of that.
Sure. Let's start with the Mage VAE. A VAE, or variational autoencoder, is basically the model's latent tokenizer.
Okay.
It compresses the raw pixel data of an image into a much smaller, denser mathematical representation before the main model even looks at it.
Right.
And the Mage VAE is designed so efficiently that the compute cost of that tokenization drops by over an order of magnitude.
Wow. And what about the rectified flow matching? Because standard diffusion usually takes a really squiggly, inefficient mathematical path to turn random noise into a clear image, right?
Exactly. Standard diffusion requires dozens or hundreds of integration steps to denoise that image.
Yeah.
Rectified flow mathematically straightens that path during training. It creates a direct, nearly linear trajectory from random noise to the target image.
Oh, I see.
Because the path is straight, the model requires far fewer steps to generate high-quality outputs during inference.
But I'm looking at the hardware optimization they used, the COD kernel fusion. From my experience, memory bottlenecks usually kill throughput long before you max out your compute cores. Is this kernel fusion essentially bypassing that VRAM bottleneck?
That is precisely what it's doing. Normally, a GPU executes a sequence of separate operations. For every operation, it has to read data from the slow global VRAM, do the math, and then write it back.
Which takes forever.
Right. Kernel fusion takes those separate mathematical operations and combines them into a single massive step at the compiler level.
Wow.
The data stays in the GPU's ultra-fast SRAM cache for the whole process. By eliminating those read-write cycles to the VRAM, MageFlow achieves a 2.5x increase in training throughput.
That's incredible. And the result is that their turbo variant generates a 1024 by 1124 resolution image in just 0.59 seconds on a single Nvidia A100.
Less than a second.
Less than a second. But the efficiency gets even wilder when we look at interactive environments with ABOT World Zero from Alibaba's AMAP CV lab. This is an action condition video world model.
The hardware specs on this are almost unbelievable. A bot world streams 720p interactive video at up to 16 frames per second on a single RTX 5090 desktop GPU.
A desktop GPU?
Yes.
Just a single 5090 with 19 gigabytes of VRAM, 1.2 second latency. That's consumer hardware running a real-time world simulation.
It is. But, the fundamental challenge with world models isn't just generating the first few frames, it's stopping the simulation from collapsing.
Right.
They solve this using a technique called long forcing.
Okay, right. Autoregressive drift. When a world model generates frames one after another, small errors compound. After a few seconds, the geometry falls apart, walls turn into water, a car merges into the pavement. How does long forcing actually fix that drift?
Well, it works by distilling a bidirectional teacher model into a causal student model.
Okay, unpack that.
Sure. A bidirectional model can look at both past and future frames to understand physical consistency. But you can't use that for real-time interaction because the future hasn't happened yet.
Right, obviously.
So a causal model only looks at the past. Long forcing aligns the causal student's long self-generated rollouts with the extended horizon logic of the teacher.
Oh, I see.
It effectively gives the real-time student model a sort of underlying intuition about the physical layout, forcing it to maintain geometry over much longer timeframes.
And if a data scientist needs even higher fidelity, the sources also detail a layer world, which scales this concept up to a 15 billion parameter video diffusion transformer.
Yeah, a layer world pushes it to 24 frames per second for interactive video. And they manage the massive memory requirements by using what they call a sync frame and geometry-aligned spatial memory.
Unpack sync frame for me. It sounds like an attention dump.
That's actually a great way to put it. In sliding window attention mechanisms, as you generate new frames, you drop the oldest frames from memory.
Right.
But those early frames often contain crucial spatial context. A sync frame is a persistent artificial token at the start of the sequence. It acts as an anchor, absorbing massive amounts of attention weights that would otherwise get discarded.
Ah!
This keeps the actual working memory clean and stable, so the geometry doesn't collapse as the video plays out. Combine that with discrete autoregressive distillation, which compresses the generation down to just 4 steps per video chunk, and you get highly efficient, stable physics.
It's just incredible how accessible these architectures are becoming. But I guess the ultimate question for you, the data scientist listening, is how do you apply this to your own ML pipelines on Monday morning?
Let's get into it.
Let's translate these breakthroughs into actionable opportunities based strictly on what we've covered today.
Okay, let's start with your internal RAGO, or Retrieval Augmented Generation pipelines. You need to stop relying on massive passive context windows to brute force your retrieval failures. Borrow the architectural concepts directly from SearchOS v1.
Okay, so actionable takeaway 1, active state management and RO.
Exactly. You can explicitly code a failure memory and a coverage map into your agent loops. Don't just let your ROG agent retry a failed semantic search. Have it vector embed exactly why it failed into a failure memory log before it formulates the next query. This actively forces the similarity search away from previous mistakes, which is going to save you a fortune in API costs by preventing infinite search loops.
That brings us to actionable takeaway 2. Cross-platform automation. I mean, data science teams spend a massive amount of time on internal data entry automation, scraping messy legacy systems, or running QA testing across different operating system environments.
And historically, you're paying a huge premium for proprietary API access to handle that logic.
Exactly.
But now, you can integrate a framework like NOAC UIClaw with an open-weight model like Kimi 2.6. You can build a highly capable, self-evolving automation agent that handles complex GUI tasks across Windows and Android entirely locally, completely circumventing those closed-source API costs.
Which is a massive budget saver.
Absolutely.
And finally, actionable takeaway number 3, which I actually think is the most disruptive, local synthetic data generation.
This ties directly back to ABOT World Deal. The ability to run an action-conditioned world model on a single RTX 5090 desktop GPU changes the math on synthetic data.
It really does.
If you are training robotics, doing reinforcement learning, or building complex simulations, you no longer need to provision an expensive cloud GPU cluster.
You can generate real-time, interactive synthetic environments locally, right at your desk. The iteration speed that provides for your reinforcement learning pipelines is just game-changing.
It fundamentally removes the hardware barrier to entry for spatial computing and physical AI modeling.
So stepping back and looking at this entire week in context, we started this deep dive talking about the macro picture. Governments and mega corporations fighting over EUV lithography, massive data centers, and multi-trillion parameter models.
Yeah, the race for raw centralized compute is literally defining international relations right now.
But at the exact same time, the most actionable, mind-bending breakthroughs we found in the sources, SearchOS v1, NOAC GIClaw, ABOT World Duel, they're all going in the exact opposite direction. They're about extreme, localized efficiency on single GPUs.
It creates a really fascinating dichotomy in the field right now. Centralized scale versus localized efficiency.
It really does. And it leaves me with this thought to leave with you. We always seem to assume that the end game of AI is a monolithic, centralized super brain controlled by a tech giant in $1 billion data center.
Right.
But looking at the efficiency of these new frameworks, could the true end game actually be hyper-optimized, highly personal, self-evolving agent ecosystems running quietly right under our desks?
That's definitely the reality these single GPU breakthroughs are pointing toward.
Something to mull over as you optimize those RAG pipelines this week. Thanks for joining us on this deep dive into the sources. We'll be back with more high-signal insights next time.